students think that this function y equals to x squared minus 8x plus 3 is just another equation. However, Cambridge thinks differently. Cambridge sees a minimum value, a range to a corresponding domain, an axis of symmetry. And I'm talking specifically about this quadratic function. A turning point, let's call a vertex, and even a transformed function from y equals to x squared to y equals to x squared minus 8x plus 3, right? So today I'm going to show you how a quadratic stops being an equation and it starts becoming a graph. And once you understand this idea, the next part, Quadratics II, which involves exam style questions as well, the part 6 in the series of functions, becomes dramatically easier. We have spent 4 lectures learning what functions are and its components like composite functions, domain, range, inverse function, transformation of functions. Today we meet the most important function in pure mathematics, which is parabolas. For example, which explains the projectile motion, how to attain maximum profit and how to attain minimum cost, and hence optimizing the business profits. So we are going to discuss today in this lecture that why do quadratics really matter. First of all, let us discuss the structure of a quadratic. So basically it is in the form of ax squared plus bx plus c. So there is an x squared term which is essential. Now b could be 0, c could be 0, and still this function would be a quadratic. What do I mean by that? So y equals to 2x squared is a quadratic, y equals to 2x squared plus 1 is a quadratic, y equals to 2x squared minus 5x is a quadratic, and hence y equals to negative 8x squared plus 5x minus 1 is also a quadratic. Now we are going to discuss that y is when a is greater than 0, the graph is going to be a minimum type, which means that graph is going to open upwards, and when a is less than 0, the graph is going to be a maximum type, which means that it is going to attain a maximum value here and go no more upwards, and it is going to open up downwards. Now first of all, let us discuss the completing the square method. Most of you already know this, but let us understand the structure of it. Now if you have a function y equals to ax squared plus bx plus c, then if you were to make x the subject in order to find the roots, then you need to do certain things, right? You need to put it into a form y equals to a times x minus h whole square plus k, right? And then you put y equals to 0 in order to, in order to find the roots of it, right? Now how do we do that? So first of all, we need to isolate x from any of its coefficients, and whatever we isolate x squared from, we do the same from the second term as well. So if I take, so what I can do is I can multiply the first and second term, multiply and divide it by a. So this becomes ax squared plus bx, and you can plus bx, and you can see that it has not really affected the structure of this function because we just multiplied and divided by a. So therefore we just multiplied it by 1. We can say that. Now if I can send this denominator here, so this becomes ax squared plus bx upon a, and this a stays here as it is, and I can copy down the c as it is. Now I can split this fraction inside the bracket by the plus sign, so this becomes a times ax squared upon a plus bx upon a plus c. So this really becomes a times, and this is how we take commons, right? Ax squared plus b upon a of x, right, plus c. Now you can see that this highlighted part inside the square bracket is nothing but part of a plus b whole square. A plus b whole square is what? Or rather, if I write x plus a whole square, what is that? That is x squared plus 2ax, and then there is another term a squared, right? Now this is missing, so what I can do is, and this part right here is half of this coefficient, right? So if this is 2a, then this is a but a square of that. So what I can do, I can really do inside of it is I can write this down as it is. So x squared plus b upon a of x. And what did I tell you just now? That if this is 2a, then this is half of that, which is a, and a square of it, right? So half of b upon a is b upon 2a whole square, because there is a square, and I can square it and then I can subtract it as well, so that I can nullify the effect of introducing something from my own, right, inside the function, right? So now multiplying and divide by a upon a doesn't affect the structure, and adding and subtracting also doesn't really affect it. Sorry, I missed this square from here. Now I can see that this can be encapsulated into a perfect square form. So this is nothing but x plus b upon 2a whole square, and this may be copied down as it is, and I close it between the square bracket as it is. Then a gets copied down as it is, and plus c gets copied down as it is. So now I can multiply this a with this function, the a outside of the square bracket, and with this function both, right? So this becomes a times x plus b upon 2a whole square minus a times, now if I square this, so this becomes b square upon 4a square, right? And I can cancel this a with one a in the denominator, and then c comes here as it is. So now I have y equals to a times x plus b upon 2a whole square minus b square plus 4a, sorry, or I can rewrite it as plus c minus b squared upon 4a, right? So now what did I tell you earlier? That we have to convert this into a form y equals to ax minus h whole square plus k. So now this part is my k. A minus h is equal to b upon 2a. So h becomes minus b upon 2a, right? And a is here as it is, right? Now, if I now try to find the roots of it, which is if I put y equals to 0, because I want to find the x-intercepts, which are the roots of a function, then I just need to put y equals to 0, and which is going to derive a quadratic formula for me, and you guys can try it on your own. I will be doing it in a bit as well. You can pause the video and try to derive it yourselves as well. Now, as you can see, and so we started this derivation from one single fact, that we have to prove that whenever this a value is greater than 0, right, then the graph is going to be a minimum type, which means that it opens upwards, and whenever a is less than 0, the graph is going to be a maximum type, which means that it opens downwards, right? Now the function has attained this form, y equals to ax plus b upon 2a whole square plus c minus b squared upon 4a. Now as you can see that for the value x is equal, if I take the value x is equal to minus b upon 2a, if I take this value, this bracket is going to become 0, right? So if this bracket becomes 0, then you multiply 0 with a, it again gives you a 0, and then you add 0 to this value, which is whatever, it could be any value, right? Minimum, max, negative, positive, 0, doesn't matter, right? So if you add a 0 to it, it doesn't change, right? So the value is going to be here. However, if you take any other value except for x is equal to minus b upon 2a, it is either going to give you inside of the bracket a positive value or a negative value. And I'm going to explain this to you with numbers as well, using numbers as well. So now whatever the value inside of it is, if you are not taking x is equal to minus b upon 2a, then squaring it gives you a positive value. As you can see that positive squared is positive, and negative squared is also going to produce a positive number. Now we are saying that a is also positive. If a is positive and the square bracket is always going to be positive, therefore this entire thing is going to be always positive. So if you're adding this positive to this number, then you are always going to get something which is greater than this, right? So the minimum value that this is going to attain is at x is equal to minus b upon 2a, which converts this bracket, which has a square over it, into a 0, right? So I can say that if a is greater than 0, then the minimum value that x is going to attain is going to be at minus b upon 2a, as you could see here, and this is going to produce me a y value, because this highlighted thing becomes 0 at x is equal to minus b upon 2a. Therefore, it is going to produce me a y value here at c minus b square upon 4a. Okay, so this is going to be a point. And now if I move here, or if I move here, because this square always turns this into a positive, and a is a positive, so when this positive bracket, when this positive number, this positive quantity gets added to this quantity, this gives me something greater than that. Therefore, the graph is going to take the upward opening shape, and hence it is going to be a minimum type. Now, let me explain using another color that if your a was negative. Now, if your a was negative, then of course, this highlighted part, the square, is always going to be negative. So the maximum value that it is going to attain is going to be at this very point, because the bracket becomes 0 at x is equal to minus b upon 2a. When you multiply that by a negative quantity outside, so 0 times anything is 0, so therefore the y value is just going to be this thing, right? Now, if y value is this, so we have all, so we can say that we have got 1 point here, right? Now, if you have gotten 1 point here, wait a second. Now what we can do is we can move to the right and to the left from here, and we can see that once the value, so if we move right from to the right, then we are going to get positive values inside the bracket, and if we move to the left, we are going to get negative values. However, when you square them, this is going to become positive, and if a is negative, like we are saying it is, then negative times positive, which is the squared quantity here, becomes negative, and negative added to this is going to produce something less than this point, right? So if it is something less than this point, therefore the quantities are going to go under it, therefore this is going to this is going to open downwards. So this is how a shape's minimum or maximum type is determined, simply by the fact that what this quantity is. If this is greater than 0, then simply we can say that the graph is a minimum type. If this quantity is less than 0, if this quantity is less than 0, then we can confidently say that the graph is going to be a maximum type and is going to open downwards. Now, we were at this point that y equals to a times x plus b upon 2a whole square plus c minus b squared upon 4a. Now, what we can do here is, in order to find the roots, if we were to find the roots of it, we have to put y equals to 0, because we want to find out where the graph cuts the x-axis, right? So these are roots. This is root 1, this is root 2. So what we can do, and this occurs at the line y equals to 0, right? At the x-axis, and this is the y-axis. So what we can do is, we can put y equals to 0 here. So this becomes a times x plus b upon 2a whole square. Now I can take LCM, so this becomes 4ac minus b squared upon 4a. Now move this here, so this becomes b squared minus 4ac upon 4a equals to a times x plus b upon 2a whole square. And now what I can do is I can divide both the sides by a, so this gets divided, this gets divided, so I get b squared minus 4ac upon 4a square. 4a square may be rewritten as 2a whole square, and this gets cancelled, and on the right hand side I get x plus b upon 2a whole square. And now if I underroot both the sides in order to towards and I will do that because I want to isolate x, so cancelling this, I get a plus and minus b squared minus 4ac, and by indices rule upon 2a whole square gives me just 2a in the denominator, and on the right hand side I have x plus b upon 2a. And now I subtract b upon 2a from both the sides in order to get the quadratic formula, which is minus b upon 2a plus and minus under root b squared minus 4ac upon 2a, and because both the denominators are same, so I can just write it down once only. So this is my quadratic formula which finds out the roots for a quadratic function, and this is it for this section. I hope that you have copied down this entire process that we did earlier, and you should be able to reproduce it as well, because now when you're given actual values and you have to find the minimum maximum points, or to find the range of a function, then you must be able to convert this into a completed square form. Now let's do an example. For example, you have y equals to 2x squared minus 5x plus 4. So the first step is to isolate x squared, and whatever you take common from x squared, you do the same from the term x. So this becomes x squared minus 5 upon 2x plus 4. Now I can see that this is the second term, 2ab, and then I must add a b squared to it, right? So this is x squared minus 5, or I can rewrite it as 2a b, and b is 5 upon 4. Now you can see that this is what? This is 5 upon 4 times 2 is 5 upon 2. So this is nothing but the same term as above, right? Now this is the b term in a plus b whole square expansion, or a minus b whole square expansion. So I can add the square of it and subtract it in order to nullify the effect of it, right? So this is called the completing the square, right? So now I have completed the square here, and because I have added something from my own, I must take it away as well in order to nullify the effect of it, of an addition, right? So now this highlighted part can be put inside a completed square bracket. So this becomes 2 times the square bracket. So this is x minus 5 upon 4 whole square, and then I put this part minus 5 upon 4 whole squared is close the square bracket, and plus 4 gets copied down as it is. So this becomes, now I multiply 2 with both the terms, this term and this term here. So this becomes y equals to 2 times x minus 5 upon 4 whole squared, and then minus 25 upon 16 gets multiplied by 2 in order to produce a minus 25 upon 8 plus 4. And now in order to take the LCM and to get a single quantity, I do this. So 32 minus 25 is just plus 7 upon 8, and this is x minus 5 upon 4 whole square times 2, and this is equal to y in a completed square form. So you can see that the minimum point is going to occur where the bracket is 0. So the bracket is going to be 0 at x is equal to 5 upon 4. So and when x takes this value, the y value that you are going to get is just 7 upon 8. So we also give it a notation h comma k. This is h, this is k, and now if you take any other value except for x is equal to 5 upon 4, you are going to get a positive quantity here. Positive quantity gets multiplied with 2 in order to give you a greater quantity than 7 upon 8. Therefore, the minimum value on y that you can get is 7 upon 8. Therefore, if the domain is given as x for all x belongs to all the real numbers, therefore you can say that the domain of function or the y values are going to be greater than and equal to 7 upon 8. So this is going to be the domain, and the corresponding range is going to be all the values greater than and equal to 7 upon 8. So if I have to draw it, first of all, it's a minimum type curve. So the value is 5 upon 4 on x, and it produces a value under 1 which is 7 upon 8, and this opens upward. Now I can also plot the y point here, so which is going to be nothing but 25 upon 8 plus 7 upon 8, so 32. So this is going to be 4. So this is going to be 4, and you can see from here as well that if I put x is equal to 0 here, this gives me a 4, right? So the graph goes here, and because it is symmetric, and we are going to discuss why it is symmetric, therefore at 10 upon 4, which is 5 upon 2, at 5 upon 2, again this is going to go here, right? The graph is going to go exactly in a symmetric fashion here and here, right? So this is also 5 upon 2 comma 4, and this is 0 comma 4, and this right in the middle is the minimum point. Okay, so this is the minimum type curve. Now why is a parabola an exact form, a quadratic curve? Now a symmetric curve. Now let's see that you have a function y equals to 2 times x minus 1 whole square plus 5. Let's take a very simple case. Now I can see that 1 comma 5 is going to be the turning point. 1, the value x is equal to 1 produces me 0 in the square bracket. So 0 times 2 is just 0. 0 plus 5 is 5. Therefore this is the minimum value. Now so at x is equal to 1, I get 5. Now, if I take x is equal to 0 or x is equal to 2, at x is equal to 0, I get minus 1 square, which is 1. 1 times 2 is 2. 2 plus 5 is 7. And if I take x is equal to 2, 2 minus 1 is also 1. 1 square is 1. 1 times 2 plus 5 is also 7. Now, if similarly, if I take x is equal to minus 1, or if I move right from this point by 2 units, likewise, I get x is equal to 3. Again, I get inside the bracket, I get either minus 2 or 2, squaring which is going to give me 4. 4 times 2 is 8. 8 plus 5 is 13. So this is going to become 13, and this is also going to become 13. So you can see that if this was 1, this is 0, this is negative 1, this is negative 2, this is 2, and this is 3. So, so the turning point was at 1 comma 5. 2, and then the other point was 2 comma 7 right here. The other point was 0 comma 7 right here, and then at 3 it was 13 somewhere here, 3 comma 13 and minus 1 comma 13. So the graph goes symmetric, right? And the axis of symmetry is going to be right here, and we already saw that this value is always minus b upon 2a. And you can also see, so minus b upon 2a. So the function was, now, so we had this function, right? So minus b, b is minus 5, so minus b is minus 5 upon 2a, a is 2, so this becomes 5 upon 4. And you can see the graph had a turning point at x is equal to 5 upon 4. Okay, so this gives us the axis of symmetry. Now, so if you have a function y equals to 2x square plus 12x minus 1, and someone asks you what is the line of, or what is the axis of symmetry, just write down x is equal to minus b upon 2a. This is a, this is b, this is c. So minus b is what? Minus b is minus 12 upon 2 times 2. So minus 12 upon 4 is minus 3. Now this, so x is equal to minus 3 is the axis of symmetry, which means that at x is equal to minus 3, we can draw a line, and the graph is going to, I don't know what the minimum point is going to be, but let's say that it is going to be here, and this is a minimum type curve. Then the graph is going to go like this, and this is going to be mirrored here as well. Okay, now let's see, let's prove, let's verify that x is equal to minus 3 is the turning point. Now for this function, if I do the completed square form, so this is going to become x squared plus 6x minus 1, and then I can rewrite it as 2 times, this becomes x plus 3 whole square minus 3 square, right, minus 1. Hopefully you guys should be able to see why I'm doing this quickly, and you would have practiced the questions from your book already, and then this 2 gets multiplied inside as well. So this is minus 18 minus 1 is minus 19. So the turning point is going to be at x is equal to negative 3 in order to give me the bracket 0, right? So minus 3 comma minus 19 is going to give me the turning point. And if I take x as 0, I get minus 1, right, as y. So the y-intercept is going to be at negative 1. So the graph is going to go like this and like this, okay? So at 6, minus 6, it is also going to be negative 1. So this is minus 6 comma negative 1. So this is for the axis of symmetry for completing the square. And now I also explained to you that why the vertex occurs at, if the form is ax minus h whole square plus k, why the vertex or the turning point is at h comma k, because at x is equal to h, this bracket becomes 0. 0 times a is 0. 0 plus k is just k. And then any other value, whether you take x plus 1, h plus 1 or h minus 1, the graph becomes negative or positive, but squaring it gives you a positive. Positive times, let's say a is positive. So positive times positive is a positive. Positive added to k gives me something greater than k. So if a is positive, then the graph is minimum. If a is positive, the graph is minimum. If a is negative, then the graph is a maximum. I would urge you guys to go to your Cambridge endorsed book by Soup and Burton and make sure that you are doing this entire chapter, chapter number 1, and doing all the questions, because everything that you guys need to understand, I've already covered. Now, there's one more thing about the range of it, right? Now, let's discuss the range. Now, if you have a function, let's say y equals to 2x minus 2 or x plus 2 whole square minus 5. So now I can see that the turning point is at 2 comma minus 5. Minus 2 comma minus 5. So this is minus 2. This is minus 5. And let's say I also give this a negative. So if a is negative, therefore, okay, let me draw this again. Now, because this is less than 0, because a is minus 2 is less than 0, therefore this is going to be a maximum curve. The turning point is going to be at minus 2 comma minus 5 because of this and this. Therefore I can draw the curve like this, minus 2 comma minus 5. So this is minus 2, this is minus 5, and the curve open downwards. Now you can see that there's not going to be any roots of this function, right? There are going to be no roots. Therefore the discriminant, which is part of the second series of this lecture, or the second lecture that I'm going to record on Friday. So we are going to do it on Friday after 2 days. Okay, so I can find out this y coordinate or the y intercept. So if I put x as 0, so this becomes 4. 2 square is 4. 4 times minus 2 is minus 8. Minus 8 minus 5 is minus 13. So this is going to be minus 13, and this point is going to be, because owing to the symmetry, so this is also going to be minus 4 comma minus 13, because if this is 2 units away, this has got to be 2 units away as well, right? Now, if let's say if I restricted the limit to x is greater than and equal to 0. If I restricted the limit to x is greater than and equal to 0, then what I'm actually saying is that I'm just considering these values of x, right? For these values of x, the validity of the graph is just this, right? So if this is the domain, then I will say that the range is going to be less than and equal to minus 13, right? So for example, if the domain was unrestricted and we said that x is true for all real values and x belongs to all the real numbers, then I would just say that, if such is the case, then y will also take all the values from here to here because it is existing on all x values. Then I would say that for this domain, my range is going to be less than and equal to minus 5. However, in the case where I restricted my domain to x is greater than and equal to 0, which was just this part, then the function that we are going to just consider is this one, which on the y values is going to produce me a range of less than and equal to minus 13. Now, before I close this lecture, I'm going to do one exam style question. So, for example, if the examiner asks you to express y equals to 4x squared minus 12x plus 13 in the form 2x plus a whole square plus b, and interpret minimum, then all you need to do is you need to, and what else you can do as well here is that you just close this, right? So this becomes, so if I just open it up, so this becomes 4x squared plus 4ax plus a squared plus b, right? Now 4x squared and 4x squared are the same, so I don't need to do anything. This minus 12x is same as plus 4a, so minus 12 is equal to plus 4a, therefore a is going to be equal to minus 3, and this thing plus 13 is same as a square plus b, so I will write down 13 is equal to a square, which is minus 3 square, from here plus b, so b is going to be equal to 13 minus 9, which is, so b is equal to 4. So I will write down that this may be rewritten as 2x plus a, and a is going to be minus 3, so I will write down 2x minus 3 whole square, and plus b is going to be equal to plus 4. Now I can take this 2 common, so this becomes 2x minus 3 upon 2, and this entire thing whole squared plus 4, and I can now square this 2 and the bracket, so this becomes 4 times x minus 3 upon 2 whole square plus 4. So now since this quantity is positive, right? So this quantity is positive, therefore this is a minimum type curve. The graph become the bracket becomes 0 at x is equal to 3 upon 2, because I just equate the bracket to 0 in order to get the x value at 3 upon 2. So the turning point is going to be at 3 upon 2 comma 4, right? So this is the vertex, this is the nature of the curve, and if they're asking you to interpret the minimum, then we are going to say that the minimum exists at 3 upon 2 comma 4, and this is a minimum type curve, and the graph is upward opening owing to the fact that 4 is greater than 0. So today we discussed what? We discussed the vertex, we discussed completed square form, we also discussed the turning points, right? You call and we also discussed the range for the corresponding domain, the corresponding range for the given domain, and the maximum or minimum type, which is the nature of the curve. So this is the nature of the curve. Should they ask you what the nature of the curve is, you will identify whether it is a maximum or a minimum type. Now in the next lecture, I am going to cover with you the following: what the discriminant is, we will derive it from the quadratic formula only. How do we find the intersections between a line and a curve, two curve? How do we find the tangents to this quadratic? How do you deal with the inequalities involving quadratics? And we are going to do some hard Cambridge style questions from past papers. Okay, so that's for the next lecture. So this was Quadratic 1, fifth lecture in the series of 6 lectures on functions, which is your chapter 1. I will now see you in the next video.